The goal of this video is to explain how to implement an FIR filter using a looping structure with an input signal buffer. You may ask, why not use the regular filter command coming out of MATLAB or the convolution command within MATLAB? Well, the reason we can't do that is because often what we're doing is filtering within a loop, and the input signal depends on some updated adaptation parameter, and so we don't have it coming in to the filtering step where you have the whole entire signal X that you can plug into the command line input for the filter. Alright, same thing goes with convolution. You don't have the entire signal X, and so you can't use the convolution command in that way. Okay, so let's take a look at how this would work, and to do so, let's start with the basics of convolution. Okay, what we know from convolution is that y of n is x of n convolved with an impulse response h of n, and the summation formula for that is that y of n is sum over all k, x of n minus k, h of k. Alright, so we're not going to get into all the details on this, but if you have a finite impulse response filter H, there's only a certain number of H's, okay? And so this infinite sum reduces down to the following. At n equals 0, you would have y of 0 is x of 0 times h of 0. I'm going to write these as subscripts. y0 is x0, h0. Okay, at n equal 1, you can look at this summation, and if it's a finite impulse response filter, y1 is x1, h0 plus x0, h1. Alright, at n equal 2, y2 is x2, h0 plus x1, h1 plus x2, h0. So you're probably seeing a pattern emerging where when you want the second output term, it's the sum of the indices that add up to 2 that would give you the second output term. Okay, so with that, you could write down n equal 3. So y3 would be x3, 3 plus 0 is 3, x2, 2 plus 1 is 3, x1, 1 plus 2 is 3, and then finally x0, 0 plus 3 is 3. Alright, so again, just to reiterate, the indices add up to the output value index. Okay, so you could keep going with that and get the output of convolution. Eventually you run out of h's, okay, and so you stop the summation at the last h term. Alright, so the code for doing that within a loop looks like the following. Okay, so the parts I want you to see is, first of all, you set up a buffer that's the length of the impulse response. Okay, then as you go through the loop, so 4k, you go from 1 all the way out to the length of x. Alright, every time you update the buffer, we're going to talk about that in a second, but basically you take the most current input sample and put it at the end of the buffer. Then you move the previous values that used to be there towards the front of the buffer. So you literally pick those up and move them. Well, you don't literally pick them up. You use the MATLAB indexing to move those to the upper end of the buffer. From there, it's a matrix multiplication. So this transpose operator is important, and what I wanted to do next is show you an example of how this works out. Okay, so here's a picture of these buffers. All right, so notice the H is written in reverse form. Okay, for n equals 0, we have the most current location of the buffer that shows up in the last location. Remember, this is a transpose, so we took the row that was X, the X buffer, and transposed it. All right, and then it's a matrix multiplication, so H3 times 0 is 0, H2 times 0 is 0, H1 times 0 is 0, and finally we get H0 times X0. All right, so that's output Y1. What happens next at n equal 1, I have that sketched out. At n equal 1, you put the most current location of the buffer into the buffer, and then you take the old buffer location, okay, so these values, and you move them to here. All right, so once you have that, it's a matrix multiplication. So H3 times 0 is 0, H2 times 0 is 0, H1 times X0, this term, that's a 1, and then H0 times X1 is the second term. Okay, so what I wanted to show you next is how to visualize this. Okay, so I'm going to select the input stacked down in a row, all right, and we're just going to verbally talk about the output values. All right, so at Y0 you have this matrix multiplication, which is like the n equals 0 case from before, X0 times H0. Okay, so that's the newest. I'm going to move this back down because this is an error. We'll get rid of that. Okay, the newest location goes in there, so let me select that again. This is n equals 0. So at n equals 0, the output is H0, X0. For n equal 1, you have this matrix multiplication, which would be H1, X0, H0, X1. N equal 2, you do the matrix multiplication. So you see, you put in the newest location, slide everything else up. Newest location, slide everything else up. Newest location, slide everything else up. So if I stopped here, this would be for n equal 5. Okay, so n equal 5, if I do the matrix multiplication, I would have that Y5 is H3, X2. I'm liking that, the indices add up to 5. Plus H2, H3, X2, H2, X3. Indices add up to 5. H1, X4. And finally, H0, X5. Okay, so that explains how this works. The thing is, the way we're doing this, we stop when we get to the end of the X values, and really if you wanted to continue on, there's an output sort of transient where the zeros come in until you empty the buffer. Okay, so that's the difference between MATLAB's filter command and MATLAB's convolution command, is the filter command stops right when the overlap stops between X and H, whereas the convolution command goes ahead and clears everything out and finishes up that output transient. Okay, so that explains how that works, and we're going to use that from now on when we have to do FIR filtering within an adaptation block.